Monday, I kind of continued talking a little bit about naming with the other group there. So I want to do kind of the same thing here, as obviously we've had some quizzes and holidays and stuff like that. So just to try to keep us a little bit back on pace and stuff like that. So we're now going to go back in the notes, like I mentioned earlier today in lecture, and kind of start talking a little bit about naming. And then we'll finish up the rest of it hopefully next week at some point. So where we left off last time with everybody, we started getting into naming. And again, we talked about the periodic table. And remember, again, things really do not have charges, as we talked about, I think, again today. Elements, they really don't have charges until they really start to combine. And it's when they start to combine with metals and non-metals is really where we get things that do have sort of the positive charge and the negative charge. And that's the basis of ionic bonding, as we talked about today as well. Again, it's always between a metal and a non-metal. And the basis of ionic bonding is we get a transfer of electrons, maybe one electron, two electrons, multiple electrons from the metal to the non-metal. The result of that is, again, the metal has more protons than electrons, becomes positively charged and what is referred to as a cation. And the non-metal picks up those electrons and becomes negatively charged because it now has more electrons than protons and becomes what is referred to as an anion. So as we emphasize today as well, there's absolutely no sharing of electrons, right, that occurs here with an ionic bond. It is a complete transfer of electrons. And again, it's that positive negative attraction, which is sometimes referred to as electrostatic attraction, that actually holds that unit together. Up here was the periodic table, I think, that we finished up on last time. And again, when these things do gain charges, these are the typical charges that they make. Everybody in group 1 is always going to be a +1. Everybody in group 2 will be a +2. Group 3, which is typically aluminum we're talking about, will be +3. Then we skip group 4, as there's really no kind of good pattern here. And then we're talking about the non-metals at this point, upper right of the staircase, -3 for group 5, -6, -2 for group 6, and -1 for group 7. Now, transition metals, which are in the middle, and these guys are actually below the staircase, they have variable types of positive charge. It does depend on who it is bound to and sort of what the charge may be. But there are 3 guys within the transition metal region. Zinc and cadmium will always make a +2 charge. And if you hang a left over there to silver, it will always make a +1 charge. So what these represent, again, are the actual charges that these guys would make when they do make a charge. And again, if they are by themselves, they will not have a charge. So that gives us formulas for anions and cations, as we have written on this page. And a reminder that when we talk about the positive cations, and if you're asked to draw the formula for a cation, you should definitely include the charge. So this is the Na plus. And how we name the positive guys is very simple. We actually just use the whole name of the metal, or the whole name of the positive guy. So Na is sodium, and this would be the sodium ion. Ca is calcium, it's group 2, so it has a +2 charge, calcium ion. Al is aluminum, it has the aluminum ion. H plus is hydrogen, which would be the hydrogen ion. Anions, which are our negatively charged guys, are different. They actually take the front part of the name of the nonmetal. We replace the last part of the nonmetal name with the IDE. So oxygen, which is group 6, is a -2. It goes from oxygen, we kind of drop most of the name, and we put IDE at the end of it, and is known as the oxide ion, IDE. Cl is chlorine, is group 7, makes a -1 charge. So we drop the last part of chlorine and becomes chloride. And hydrogen is the only weird one in the sense it can go positive. It can also be negative in certain cases. And again, that would be the hydride ion in that particular case. Any questions on that stuff we, I think, talked about last time during lecture? Okay, then let us get into some of this naming here. So we're really going to focus in first off on what is sometimes referred to as type 1 or type 2 compounds. And these type of compounds are definitely ionic compounds. And again, that basically means, as we've been talking about pretty much today, that is our metal and non-metal. And whenever you go about trying to name something that is a metal or non-metal together, the most important one out of those two is actually the metal. That is the most important guy to look at. It is the metal that will actually tell you how you are going to name this particular compound. And type 1 guys are where the metal is sodium, calcium. Basically, the metal is from group 1, 2, 3 are its zinc, cadmium, or silver. And if you remember, what all these guys pretty much have in common is they all have fixed charges. As we talked about, sodium is group 1. So no matter what the situation, sodium will always be group 1. And that's how you can recognize it as a type 1 compound, because it contains a metal that comes from group 1 on the periodic table, group 2, group 3 are zinc, cadmium, silver. Type 2 ionic compounds, the metal's also what you're looking at, but the metal basically comes from the transition metal, except for obviously zinc, cadmium, and silver, are just to the right. And what I mean by that is, if you look at the periodic table, this is our transition metal region. We have the staircase that comes down. So all of our transition metals, except for zinc, cadmium, and silver, have variable charges. And then also in this region below the staircase, where we see things like lead or tin or antimony or bismuth, these guys, which are technically not transition metals, also have the ability to make a variable charge. And what we mean by that is, in certain cases, copper, for example, as we see here, certain cases copper will be +1, and some cases copper may be +2. Chromium, for example, which is Cr, again, in certain cases, chromium may be +2 or +3. It really does depend on what it is sort of bound to. How we go about naming these guys are very similar to each other, but depending on what type of metal you're dealing with, there is a slight difference as to what you need to do. Now, before we continue on, just to make sure, I think we talked about today, and I think we talked about last time, but just to make sure, remember that when we take an ionic compound and we want to write the formula for it, the overall charge needs to equal 0. What I mean by that is the positive charge of the cation needs to balance out the negative charge of the anion. So I think earlier we looked at calcium with fluorine or fluoride. Again, here, if we were just to put those two guys together, +2 and -1 gives you a +1 charge, which is not good. And that is why when we put them together, we actually need 2 of the F minuses. And the real reason for that is what we talked about earlier, that it gets everybody to that noble gas configuration. That way, when we put it together, we do write a formula that has no charge. So the formula for ionic compounds should definitely have no charge. But if you were to write what really makes this up, this is really made up of a cation that is calcium with a +2 charge and an anion that is fluorine with a -1 charge. So when we write formulas for ionic compounds, they do not have charges, even though they technically are made up of things that actually do have charges. Again, same idea with like sodium chloride. Absolutely no charge written there in the formula, but it is actually made up of 2 things that do have charges, a cation that is sodium with a +1 charge, and an anion, which is chlorine there or chloride with a -1 charge. So important thing is, and really based on what we were talking about today with bonding, the idea is we always want to put together anything that's positive and negative in the simplest way to get to an overall charge of 0. There's many ways you could get to 0, but you want to always do it in the simplest way that gets you to 0. Any questions on that there? So here again is some examples of what we talked about. Again, anything that's positively charged, pretty simple and straightforward. We're just going to use the whole name of the element. Anything with the negative charge from the periodic table, drop the last part of the name. And again, those guys get the IDE treatment. So let's talk about type 1 compounds here and sort of how we go about naming them. Again, it's pretty straightforward in terms of type 1. Again, we're looking at the metal. And if it is in group 1, 2, or 3, so that metal is most important. And group 1, 2, 3, zinc, cadmium, or silver. Pretty much the way we name it is we use the whole name of the metal. And the non-metal gets the IDE treatment at the end of it, and we drop the last part. So when we look at something like NaCl, we first see Na is a metal, Cl is a non-metal. That automatically should tell us it is a ionic compound. We then want to always look at the metal, and we see that the sodium comes from group 1, which tells us it's a type 1 compound. At that point, we don't have to worry about anything other than following these rules. So the metal's name is sodium. The non-metal's name is chlorine. We drop the last part, and it becomes sodium chloride. If we look at something like CaCl2, we could do the same sort of procedure here. We see calcium, which is a metal. We see Cl, which is a non-metal. Again, that combination tells us it's ionic. We always want to look at the metal. We see calcium's in group 2, which tells us it's type 1, and that's it. We are ready to name. We just call this calcium, whole name of the metal. The non-metal gets the IDE here. Now, a very common mistake that people want to make, and perhaps somebody's maybe thinking about asking that question is it dichloride because there's 2 of them? And the answer is no. You do not use any type of prefixes here. The number that we see on the bottom there has absolutely no effect on the name. You could have 40 of them. You would still just call it chloride. So this is calcium chloride. It is not very commonly mistakenly identified as calcium dichloride. You do not use prefixes in type 1 naming. And again, the reason for the 2 is, as we talked about earlier, calcium is the cation here. The anion is Cl minus. And again, if we put these together, we would need a second chloride. And that is what the 2 represents, that there are 2 Cls, each at -1, which gives us a grand total of -2 to balance out the +2 charge that we see on the calcium. Any questions on that there?
Professor, I have a quick question regarding that where it says metal groups 1. What is I can't make out what's after the 3.
That's zinc.
Zinc, okay.
Yeah, zinc, cadmium, and silver. So if you look on the periodic table right around 30, that should be zinc. Right below it should be cadmium.
Okay.
And go left to silver. And these guys are transition metals, but they actually have fixed charges. So they're considered type 1 metals. You would not use a Roman numeral or anything like that with it. You would just name it like this because they are fixed.
All right, thank you.
You're welcome. Other questions? Okay. So as I mentioned a second ago, we always want to, when we write the formula for an ionic compound, always make sure that the charge equals 0. The actual formula for the compound should never have charges like we see here. Again, if we look at this, we see potassium, which is a metal. We see I, which is iodine, is a nonmetal. That again should scream ionic to you. We look at the metal, which is potassium. We see that is group 1, which is this is a type 1 compound. That means we would proceed to the whole name of the metal, which is potassium. And the nonmetal, we get the IDE at the end of it, which would become iodide. So although Ki, again, does not have an overall charge, it is, again, still made up of two things that do have charges: a cation that's K plus because it's group 1, and an anion that is I minus and group 7. All right, so let's take a look at a couple of these guys here and see how we come about the names. Again, looking at this, I see potassium, which is a metal. I see Cl, which is a nonmetal. That again tells me ionic. We look at the metal always. That is potassium, which is group 1. That tells me it's type 1. And that tells me that's all I need to know. We're going to use the whole name of the metal, which is potassium. The chlorine then becomes chloride, the IDE at the end of it. And that is all she wrote there on that one. Any questions on that one? Same thing here. We want to really dissect what we're looking at. We see calcium, which is a metal. We see Br, which is a non-metal. Again, that tells us ionic. Focusing on the metal part, which is always the important guy. That is group 2 in this case. Also tells us it's a type 1, which means at this point we could proceed to naming whole name of the metal, which is calcium. The bromine becomes bromide, IDE at the end of it. Again, we see that there are 2 of them because it is a cation that is Ca2 plus and an anion that is Br minus. Again, if we were to put these together, we need not one of these guys, but 2 of them. We need it in the formula, but we do not do anything with that 2 in terms of the name. And again, no prefixes here. Same thing here with our top one. Our cation here is our K plus. Our anion is our Cl minus. Again, when we put these together, +1 -1, which is why we just have one of each of those guys. And again, that's how we get to that. This is an interesting one. This is Ba, which is a metal. Remember that hydrogen is actually a non-metal. So again, this tells us ionic. Looking at barium, which is group 2, tells us it's type 1. That's all we need to name it. We would use the whole name, which is barium. And hydrogen actually becomes the IDE version of it, and it is barium hydride. And that is because in this particular case, the cation is barium with a +2. The anion here is hydrogen with a -1 in this case. And that's also why we have not one of those guys, but we actually have 2 of those guys. This is really the case where you will probably only see hydrogen as a negative charge is when it follows a metal in a compound. If hydrogen comes first, for example, like HBr, even though technically they're both nonmetals, hydrogen is almost sort of named like a metal, a type 1 metal. And basically what this is a cation that is H plus and an anion that is Br minus. And that's why when we put it together, we just need one of each of those equals 0. We actually follow kind of the same rules when you have hydrogen. Again, hydrogen is a little bit, has some different properties, but we would actually just call this hydrogen bromide. So hydrogen a little bit different if it comes in front. Even if there's multiple ones that come in front, hydrogens, we still just call it hydrogen and whatever the negative guy is. Question on those guys there. All right, so why don't you try some here? Let's do why don't we do MG? Let's do MGI2. Give the name of that guy. Let's do AL203. Give the name of that guy. And let's do Li2S. Give the name of that guy. And we also, I'm going to give you some names. See if you can write the formulas. Let's do sodium oxide. Let's do barium. See what this barium chloride over there. Let's do barium. Actually, let's do barium nitride. And lastly, let's do aluminum chloride. All right, take a couple minutes here. Guys on the left, proper name. Guys on the right, proper formulas. Okay, let's take a look and see how we're progressing here. So we'll start with the guys on the left there and really just want to focus, same thing. It's good to dissect what you got going. We see magnesium, which is a metal. We see iodine, which is a non-metal. Again, tells us it's ionic. Always want to look at the metal part of it. We see magnesium, which is group number 2. That tells us it's a type 1 compound. And that means that's all we need. So I think I'll go underneath. We'll use the whole name of the metal, which would be magnesium. The iodine gets the IDE at the end of it, and it's iodide. Again, the 2 here has no effect on it. It is there because of balancing out the charge, because the cation is magnesium, the +2 charge. The anion is iodide with a -1 charge. Again, we need 2 of those to balance out the overall charge, but again, has no effect on the actual naming. Any questions on that one there? Looking at the second one, same deal. We see Al, which is aluminum. That's a metal. Oxygen is O, which is a non-metal. Again, tells us ionic. Focusing in on the metal part, that is aluminum, which is group 3, and aluminum always has a fixed charge of +3. So that tells us it's type 1, and that's all we need for the naming aspect of it. This would then be aluminum, whole name of the metal. Oxygen now becomes oxide. Again, here the 3 has no effect on the name, nor does the 2. So this is not like dialuminum or trioxide. Again, no prefixes should be used here. They have no effect on the name. The reason for the numbers, again, is because aluminum is the cation that has a +3 charge, and we need 2 of them to get us +6 to balance out the 3 oxygens that we need to get us to -6. So -6 and +6 equals 0, which is what we want for the formula here. Any questions on that one there? Lastly, looking up here, we got Li, which is lithium, which is a metal. We have S, which is sulfur, which is a non-metal. So again, rings the ionic bell. The metal, which is the important guy here, is lithium, which is group 1. Rings the type 1 bell there. And that's all we need. Again, lithium, whole name of the metal, even though there's a 2 there, not going to affect the name. Sulfur becomes sulfide, IDE at the end of it. Again, this is made up of a lithium cation that's positively 1 charge and a sulfide ion, which is -2 charge. That is why we need the 2 lithiums to balance out the -2 charge from the sulfur. Any questions on any of those names?
Professor, I'm sorry. Can
Yeah.
you explain or um, up at the top, the A13 plus A13 plus 6.
Yeah, so basically the basic units of aluminum oxide, the cation is group 3, which has a +3 charge, right?
Let me see, group 3. Oh, okay, 13.
Yep.
Okay.
So yeah, so we go by the representative numbering. So we call that group 3 where aluminum is.
Okay.
And it's the A numbering. And because it's group 3, it has a +3 charge. The anion here is oxygen, which is group 6, and that is a -2 charge. So these are the basic 2 units that make up aluminum oxide.
Mm-hmm.
Now, always when we take a positively charged ion and a negatively charged ion, the goal is to put them together in the simplest way that will get you a 0 charge overall, which basically means all of the positive charges will balance out all the negative charges. So in this case, we have a +3 and a -2. The common number between 3 and 2 is 6. And you can get that by simply just multiplying those numbers together. It gives you kind of like the common number between them. So the goal here is now to get each of them to really a 6 overall charge. So one aluminum is +3. So we need not just one of those aluminums, but we actually need 2 of them. And that will give us an overall charge of +6. And that's why the formula will represent Al2. And basically that 2 means that we have one aluminum that has a +3 charge and one more aluminum that has a +3 charge. So +3 and +3 gives us +6. Now we need to now get our oxygen here, our oxide, to -6 to balance it out, because +6 and -6 equals 0. So if you add +6 positives and 6 negatives, it equals 0. Each individual oxygen has a -2 charge. So we need not one of them, not 2 of them, but we actually need 3 of them. 3 times -2 gives us a -6 overall charge. And that's what the 3 represents. So we have 3 individual oxide or oxygen ions that have a -2 charge. So when we now take the +6 from the 2 aluminums and add it to the -6 for the 3 oxygens, we now have an overall charge of 0, which is what we want when we put our formula together.
Oh, got it. Oh, okay, appreciate it. Thank you.
And that's the goal when you do any type of ionic formula. You always want all the positives and negatives to balance out to 0. And the simplest way to do that. Now, sometimes people will teach you a trick like what you could do is just simply take the charge down there and the charge down there, and the 2 comes down, the 3 goes over there. Or you could do it opposite, bring the 2 up that way, bring the 3 up that way. And it does work. It does work about 92% of the time-ish. It doesn't work 100% of the time. So it's best to think about this again, kind of like what I've been doing, like what we did here with the calcium and the bromide. Calcium has a +2. So to balance it out, we need 2 of these negative guys. And that gives us our correct formula, CaBr2. If you kind of do the crossover thing, which is very commonly taught, it will not work 100% of the time. It will work a lot of the time, but not 100% of the time. So it's good to think about it in terms of like balancing out charges. Other questions on that?
Thank you, Professor.
Yep. Okay, so what do we do if we have the name and we want the formula? Well, simply, it's actually what we just did here. The goal is you just really want to start with the basic ions that make up this ionic compound, and then you want to put it together so that you equal 0. So when we see sodium, we know sodium is group 1, which means the basic cation that's there is a sodium with a +1 charge because it's group 1. Oxide is oxygen, which is group 6. And everybody in group 6 makes a -2 charge. So our goal at this point is to put these guys together in the simplest way that will get us to 0. And hopefully you can see that you actually need one more sodium there to balance out the -2. So the -2 from the oxygen is now balanced out by the 2 individual sodium ions. And now we just need to write what we did. That is Na2 and O. The 2 represents 2 sodium ions with a +1 charge and 1 oxygen ion with a -2 charge. Again, +2 and -2 equals 0. Any questions on that formula there? Working the same thing here with barium nitride. Barium is group 2, which means it has a +2 charge. Nitride is nitrogen, which is group 5, which means it has a -3 charge. So now again, when we put this together, a simple way to figure out what we're looking for is just to basically multiply these two numbers. 3 times 2 is 6. So that is the common number that will get us to 0. So to get our barium to 0, each one is +2, which means we would need not 1 barium with a +2, not 2 bariums with a +2, but we would actually need 3 of these bariums, each with a +2 charge, which gets us to +6 overall. To get our nitrogen to -6 to balance it out, because each one is -3, we need not 1 of them, but we need 2 of them to get us to -6. -6 and +6 means we are now at 0. At this point, you can just simply count what you got there. That is 1, 2, 3 bariums, which means we should write Ba with a 3 on the bottom. And we have 1, 2 nitrogens, which means we should basically write 2 nitrogens. And there you go. That should be the correct formula on that one. Any questions on that? All right, last one there is aluminum chloride. Aluminum is group 3, and I'm running out of room here on this slide. We'll erase something here so I got something to write on. Let's get rid of this here. We'll write it over here. All right, so aluminum is group 3 on the periodic table. So we know it has a +3 charge. Chloride is chlorine, which is group 7 on the periodic table, which has a -1 charge. Again, the goal here is to put these together to equal 0. So I have +3 and -1. Again, if you just multiply those two, 3 times -1 or 3 times 1 is 3. The aluminum's already at 3, so I don't need any more of those. To get the Cl- to 3, I need 1, 2, and 3 of them. That gives me 1 aluminum and 1, 2, 3 chlorides. And that would be the correct formula. Any questions on how to go from formula to name or name to formula? All these guys here are, again, type 1 ionic compounds. Any questions on that?
I have a question. It's not on that. I just wanted to know how do you know the charge of the element? Like for chlorine, you put it was just a -1. So how do you figure that out?
We talked about it a little bit earlier there on.
Sorry.
It was, where is that? Was here, I think, right here. So there are certain elements and stuff on the periodic table that have fixed charges that when they do make a charge, they will always make a certain type of charge. So everybody in group 1 will be +1. Everybody in group 2 will be +2. Group 3, which is basically aluminum, will always be +3. Then group 5, which is our non-metals, where they become negatively charged, -3, -2, and -1 for group 5, 6, and 7. And that's why, for example, when we said oxygen, which is in this group, we know that when it makes a charge, it will be a -2. And for example, when we did like lithium, we know it's in this group and it will always make a +1 charge. So there's certain things that have fixed charges, and that's how you kind of know where the charges are. The exception is that also have fixed charges is the zinc and cadmium is +2 and the silver is +1. So this is a really important thing to remember. It will help you kind of quickly know the charges of those kind of things.
So Professor, everything on group 6 will be a -2 charge?
It would be, and again, we're talking really about the non-metals that are above this.
Yes, the non-metals.
Yeah. So again, the metalloids are below that are metals would not be, but just the non-metals. So remember, the non-metals are the guys that will make those negative charges. So
Yes.
kind of like up and to the right of that staircase is really the ones that we're talking about.
So it'd just be groups 5, 6, and 7, right?
Yes, so 5 is -3, 6 is -2, and 7 is -1. 8 is the noble gases, so they're not interested in bonding or anything like that. So
Okay.
it's fine like there is. And there's no real good pattern in group 4 because on the top you got like non-metals, you got a lot of metalloids, and you got metals on the bottom. So there's a lot going on in group 4.
Okay.
There's no real good pattern. So a good way to remember it is to go kind of like +1, +2, +3, skip, and then go backwards. -3, -2, -1.
Okay.
And that's a good way to remember it.
So arsenic would be a -3, right?
Yeah, so we're as long as it's, again,
Above the staircase, right?
yeah, above the staircase, not part of the staircase, not part of the metalloids, and
Mhm.
then it would be a -3. Yeah,
Okay, cool. Thank you.
you're welcome. Okay, so that is type 1. Let us, Jacob, that answer your question? Yeah.
Yeah, thank you so much. Sorry about that.
No worries, it's all good. All right, let's talk then about type 2 here. Where are we at there? And that little chart that we just looked at is going to be very helpful here with type 2 compounds. So what is the difference between type 1 and type 2? There is not really much of a difference. They are both ionic compounds. Type 2 compounds are also a metal and a non-metal. And just like type 1, it is the metal that's really important. The difference, though, is that that metal will be a transition metal, or again, just to the right, underneath the staircase. So again, where you see things like lead, tin, antimony, bismuth, in that general area, which is sort of like below the staircase there, kind of to the right of the transition metals on the periodic table. Those guys can have variable charges. So how do we go about naming these guys? We actually go about naming them the exact same way. We use the whole name of the metal, just like we do in type 1. We use the non-metal that ends in IDE, just like we do in type 1. But the difference is because these metals can have different types of charges, like copper could be +1 in certain situations, copper could be +2 in other situations. You need to kind of tell the person that's looking at it that in this case, we're talking about copper with a +1 charge. In this case, we're talking about copper with a +2 charge. We include a Roman numeral. And the Roman numeral is the positive charge on one metal ion. So if you took out the metal ion by itself, what the positive charge is. Now, if we look at something like this, we want to kind of analyze it the same way. We see FeCl2. Fe is iron, and we know that's a metal. We see Cl, which is chlorine, which is a non-metal. So again, automatically that tells us, like it did in type 1, that it's ionic. It is the metal that's most important. And in this case, it's iron. So if we look at the periodic table, we will find iron right there in the middle of the transition metals. And that automatically should signal to you that it is a type 2 compound. And you may not know what the charge is on the iron. So the good news is you will always know the charge that it is attached to. So whatever non-metal is attached to that metal, you will always know the charge. And that's where that chart we were just looking at is also really important here. Because if we look at that chart, we can see that Cl is group number 7, which means it should have a -1 charge. And there's not just one Cl, there's actually 2, which gives us a grand total of -2. there's actually only one iron present here. So to balance out the -2 charge that's being supplied by the two Cls, this iron will have to have a +2 charge. So how does that translate to our name? We again use the whole name of the metal, which is iron. Because iron can be +2 or +3, for example, we use the Roman numeral 2, not to tell us how many iron atoms we have, but to tell us what the actual positive charge is on the iron. And the last part here, this non-metal is named just like we did in type 1. Even though there's two of them, it would still be called just chloride, no prefixes. So this would be iron Roman numeral 2 chloride. And the reason we need to do that is because, for example, if we had FeCl3, looks very similar to the one we just did. Again, we have iron, which is a metal. We have Cl, which is a non-metal, which tells us it's ionic. The iron is still a transition metal, which tells us it's a type 2. So now we need to figure out what is the charge on it. So we have one iron atom. In this particular case, we still have Cl, which is -1, but we actually have 3 Cls in this case, which gives us a grand total of -3, which means to balance out the iron must be +3. And now that gets incorporated into the name as iron, whole name of the metal, Roman numeral 3. Again, not how many irons we have, but the actual positive charge on it. And even though there are 3 chlorides here, it is still just named chloride. Iron Roman numeral 2 chloride tells us we are dealing with iron that has a +2 charge. Iron Roman numeral 3 chloride tells us we are dealing in that case with the iron that has a +3 charge. Question on that?
So, Professor, how high could we go on the Roman numerals? Does that vary on the?
As high as the charge, I would say probably in most cases, maybe +4 might be as high as you see, or Roman numeral 4. Maybe
Okay.
you could go 6. I mean, it can go 6 or so, some things, but probably for our class, I would anticipate 4 or 6 in terms of Roman numeral would probably be, as high as you would go. So for example, I think the next one, if we look at it, and then we'll finish up here for today. If we look at PbO2, when we look at this PB is lead. And we look at lead, that is a metal. Oxygen is a non-metal. And if we look at the location of where lead is, it is really underneath the staircase. It is really to the right of the transition metals, but something like lead can have a variable charge, which makes lead a type 2 compound. So we would approach it the same way. Lead at this point, we're not really sure what the charge is on it, but the good news is we do know what the charge is on oxygen. Oxygen is group number 6, and group number 6 has a -2 charge, which means we have not just one of those, but because of the formula, we actually have 2 of them. So if we just add up the negative charge here on the oxygens, that is a grand total of -4. There's only one lead here, which means to balance it out, it does have to be +4 to balance it out to get us to 0. Remember, we're still at the goal here to get positive negatives to equal 0. And now in terms of our name, we would use the whole name of the metal, which is lead. The Roman numeral here would be 4 because the positive charge is 4. And again, even though we have 2 oxygens, this guy would be called oxide. Question on that name?
Okay, so the positive charge just basically has to cancel out the negative charge, correct?
Yeah, so it goes back to the basic thing that we were talking about
Yes.
since the beginning here, that always when you put a positive guy and a negative guy together, and that always happens in an ionic compound, when you put those 2 ions together, the charge needs to equal 0 in the simplest way possible. So all the positive charge has to be balanced out by all the negative charge on the anions, and the cations need to balance each other out.
Okay, thank you.
You're welcome. Other questions on that?
So Professor, you would be asking us what type of question on this? This would be,
This would be one of two things, kind of like what we just did on the other one as well. You might either be given the formula like the PbO2 and ask what is the name, or you may be given the name and ask what is the formula. So one of those two ways. You need to be able to kind of do it both ways. Go from the formula and give the proper name. And then if you're given the name, be able to give the proper formula for it. So kind of go both ways, like we did in the previous example.
okay, thank you.
You're welcome. Other questions on that? This would be one case where we talked briefly about doing the crossover move. And this would be a case where you would not get the right answer here. If you crossed over the 1, you would get like an oxygen with a -1 charge and a lead with a +2 charge, which is incorrect. So as I mentioned before, sometimes your people are taught to do kind of the crossover, move the charge down, and that'll give you the subscripts and move the subscripts up. And again, it doesn't work 100% of the time. It works a good number of times, but it's best to kind of think about like we've been doing here, balancing out the overall positive and negative charge. Other questions on that? Okay, so we will lay it up here for discussion. We obviously will continue this